Hello everyone, welcome to my YouTube channel. Today we are going to discuss about variations of physical properties from bulk to thin films to nanostructures. So similarly what we discussed about introduction for the previous class for length scale, the same information will also act as an introduction for this topic also, because that was also the reduction. Actually, it's a continuation of a fourth topic, that is variations of physical properties, how the physical properties are changing from bulk to the thin films or to the nanostructures. The introduction remains the same thing. Nanotechnology has a great impact on every field of science and technology, as we discussed in the previous class, as materials gains extraordinary properties when reduced from bulk to the nanoscale. So bulk materials, when they are reduced less than 200 nanometer, which this scale 1 to 100 nanometer or 1 to 200 nanometer, this falls under between the molecular scale and the atomic scale, and that's where the science changes, actually the physics changes. Actually that's why the properties changes, because materials behave strangely. Okay, so here are some of the examples I can give. So 1 nanometer is nothing but 1 billionth of 1 meter, that means 1 billion times less than 1 meter. Okay, the width of an hair is around 100,000 nanometers. The diameter of the one hair I'm talking about 100,000 nanometer. That means in that our hair diameter we can fit 100,000 nanoparticles. Okay, human blood cells are around 2,000 to 5,000 nanometer long. Okay, just blood cells, not the whole blood. Okay, and a strand of DNA has a diameter of 2.5 nanometer that we just saw in the previous class with the comparison with the length scale. Next, a line of 10 hydrogen atom is 1 nanometer. If you are keeping 10 hydrogen atom, you are going to get 1 nanometer. So imagine that's how the nanotechnology is related to. Okay, so here the example is there. If the area is around 6 centimeters square in this whole box, if I cut it into the 2 pieces, then I will get around 12, and then 4 pieces, then 24, and if I am cutting it into the number of spaces, a number of area we are going to get. So how we are going to increase here? See, total surface area, total the space, how much it is taking is same, but the area is increasing. Why? This is here also, whatever the box is there, same box is here, area is increasing. Why? Because when I cut this block into 4 pieces or 2 pieces, the internal space is open now. Now the internal space also we have to count, right? Again, when there are 6 faces, that is 6 centimeter. And when I cut into this thing, I will be getting around in 4 sections, I will be getting around 12 centimeter. 12. Why? Because I got, once I cut into half, I got 2 blocks now. Okay, inside 2 meter extra area I got. Right? It was close. Now I cut it. So inside internal space is now outer space. So that extra space is added. Similarly, it is keep on going. Okay, like this. So size and property relationship of nanoparticles. So we are having macro or micro particles. If you convert that into the that can be converted into the nanoparticles. So increase in the surface area to volume ratio. So one of the major property of nanostructures, which is helping in almost every field, is that the nanomaterials exhibit high surface to volume ratio. Why high surface to volume ratio? As the material keep on decreasing, its volume keep on decreasing, right? As the materials keep on reducing from macro to the micro to the nanoparticles, so volume keeps on decreasing. Once the volume keeps on decreasing, surface keeps on exposing. So when the surface is more compared to the volume, that is why we are calling it as surface on the numerator, and the denominator we are having volume. Surface to volume ratio is high. Why? That means the volume is less, the surface area will be more compared to that, in relation to that. That the ratio will be always high. The surface to volume ratio is very high in nanomaterials. So how it will be helpful? Because if the surface is more, that means the surface atoms are more. If the surface atoms are means the activity, any activity in a material takes place at the surface. So the more activity, more the surface, more the activity. As simple as that. So increasing dominance of quantum effects. So once you have the higher surface area, then the quantum effects will be more. The dominance of quantum effects will be more. That's why the properties changes, right? So increasing the dominance of surface of a particles over that of those interior. That means whatever the particles were there inside, okay, are less. Whatever the particles are there exposed outside are more. That's why we are getting the strange properties here. Why? Because more surface atoms compared to the inner surface atoms. So definitely its properties has to change. That's how it's changing. That's why the surface to volume ratio is one of the major property in the nanostructure or nanomaterials, which is having a lot of applications. So high surface area is the key for catalyst for catalysis to medicine. You take, for example, medicine, you take any kind of reactions, you need surface. For that, nanostructures has got a huge surface. Okay, that's why we just saw that from here to here how much surface and surface area. Once every block is at nanoscale, we will be getting around 2.5 acres from just 6 meter square or centimeter square blocks or area. So that was about the surface theorem. This is how it is in diagrammatically we can explain in these atoms, outside atoms are surface atoms, inner atoms are inner atoms which are not exposed, right? So now we will see how the nanostructures are getting more surface area or surface to volume ratio, why it is increasing. Or if I am asking you like prove that nanomaterials has got high surface to volume ratio, this is how we can prove. So you can take a beaker which has got a bulk structure here. Example, the surface atoms, imagine there are 18 atoms are there and inner atoms are there, 12 are there. So here the ratio is 1.5. So now again I am reducing it to the some extent. So now the surface atoms are 14. Obviously atoms will not be just 14, it will be in a number. I am just giving you an example. So imagine, so now it is reduced to from outer 14 are there, inner 6 are there. So as you keep on reducing, then the inner atoms will reduce. So 14 divided by 6, so you will be getting how much? 2.3. Now the surface ratio, surface to volume ratio is increased or not, from 1.5 to 2.3. Now again I am reducing it. So here only 2 inner atoms, rest all are outer atoms. So in this case the surface volume ratio is 5. So compared to 1.5 to 5, which is higher, 5. So as you keep on reducing the size, you are getting the better surface to volume ratio. Hence proved. So basic types of the large scale nanomaterials are there from the bulk forms. The filler materials, whether 0-dimensional, 1-dimensional, 2-dimensional nanomaterials, they are used to make films, okay, like thin films and bulk nanostructures. We are having large scale form, we are having basic geometry of 0-dimensional is something what it looks like this, and the diameter for the nanostructure 0-dimensional we are having 100 nanometer. Now I am using this example is quantum dots. Now I am using this 0-dimensional nanomaterial and I am making thin film out of it. So all the quantum dots, around thousands of quantum dots is fit into the one sheet, and here thickness will be nanoscale. Okay, so imagine 10 nanometer one quantum dot is there. So I am using 100 quantum dots, so it will exceed in the microns, maybe the 1000 nanometer. So that won't be, now the particles dimensions are not in nanoscale, but one dimension is in nanoscale, that is the thickness. Okay, so I can call it as nanocomposite thin film. From there to the bulk nanocomposites. This is where we are getting this topic, right? See here, what is our topic? Variation from physical properties from bulk to the thin films to the nanostructure. Bulk to the thin film to the nanostructure. Bulk to the thin film to the nanostructure. So here, next, speaking that was about 0-dimensional. So for 1 dimension, we are having like wires, nanorods, nanotubes, all these things. Okay, and here the diameter will be 100 or less than that. So here we can use the carbon nanotubes, and I can align into a particular shape in a particular this thing, then I can get a nanocomposite thick film, which will have one diameter will be the nanostructure, or maybe more than that. So with the help of this only I am creating more and more. I am getting bulk nanocomposites, which contains billions of carbon nanowires or nanorods or nanotubes, understanding. So that will be our not just a bulk composite, but bulk nanocomposite. Next we are having two dimensional. We are having a graphene sheet here, or any silicon sheet, or any atoms you take, and you can prepare that particular sheet. If we want silicon sheet, take the silicon atom as the raw material. Okay, go for nanomaterials production production tools or techniques, and when you introduce there, and maybe because of CVD, PVD, laser or inert gas condensation or those kind of things, then it will eject all the atoms and it will go and deposit on the this thing, thin film, and it becomes the thin film on substrate. Next, that's how the bulk nanostructures, which contains lot of thin films here, a number of thin films, maybe billions of thin films, understanding. That's how from zero dimensional to the thin films and to the bulk nanostructures, or bulk to the thin films to the nanoparticles. So one more example why this particular scale, the properties, how it changes from bulk to the nanostructure. So imagine 1 meter square. So here 1 meter square box, in square in the box, square box, how many faces will be there? 6. So 6 into 1 meter square. So your total area is how much? 6 meter square. Now I cut into like this. So when I cut into like this, so you can write here, instead of 1 meter, you can write it's half meter now, right? But how many box I got? Around 8 boxes. 1, 2, 3, 4, 5, 6, 7, 8, right? So that will be giving me the 12 meter square. That is almost, the area is doubled when I cut into 4 pieces or 8 pieces. When I cut into 16 pieces, okay, so now that will be 1 by 3, so that will be around 27 pieces, okay, 3, 3, 3, in 1, 3, 3 into 3, 3 into 3, so total 27. So 27, that will be giving me again 6 more added, so 18. So like that, if you keep on continuing and reducing, and here 1 divided by 10,000 millimeter, that is almost something going to the blocks are going to be in 0.1 millimeter. So, or that is nothing but around 1000 nanometer, or maybe 100 nanometer. So 1 to 100 or 100 less than, consider it as 100 nanometer. So you will be getting the surface area to 2.5 acres. Now I am asking you whether the whole the volume is changed. No, here the volume is the same thing. 1 meter square is the same area actually, but I am exploiting this all the surface area which is hidden. So as soon as I am reducing it to the nanoscale, this 6 meter square area can be converted into 2.5 acres. Now if you have land and all, you can just see how much 1 acre means. Okay, it is nothing but 40 guntas, right? So it will be having so much this thing, right? So like that. So 1 cents is equal to 2.5 guntas, and that will be supposed to be around 40 means around maybe around 15 or 16 cents of area. You can get it in just from the 6 meter square block. So that's the beauty of nanostructures. As we are reducing, we can fit a lot of 2.5 acres in 1 meter square box or 6 meter square area of the box. Okay, that's how the things works at nanoscale. Next topic, we are having surface to volume ratio, which is again with the same example we are going to explain or prove. Okay, as the surface particles are reducing, the surface will be increasing. That will be in the next class.